Jnanam Paramam Dheyam. Knowledge is supreme.
So, welcome to today's lecture. We will just recall what we had done last time and then describe what we will be doing today. If you recall, last time we looked at how to find inverse of a matrix, and we proved a theorem, namely that a square matrix is invertible if and only if its reduced row echelon form is identity matrix. And we also give a algorithm of finding the inverse in that case. So, this was the theorem that we proved last time, that a n cross n matrix is invertible if and only if it has full rank, that is the rank of the matrix is n, and that is equivalent to saying that the reduced row echelon form is identity. And that process of converting the matrix to reduced row echelon form also gives you a way of finding the inverse. So, today we are going to look at another concept called determinants of a matrix, and which will also relate it to invertibility of the matrix. So, to motivate what is determinant, you all must have been using this concept in your school curriculum, and how to compute determinant of something 2 by 2, 3 by 3. So, we will start with looking at why a determinant has that properties and what are the minimal set of properties that define determinant. So, we start looking at the concept of geometry, namely finding the area of a parallelogram. So, suppose we are given a parallelogram with defined by two vertices, OA is one vector, OA is one vector and OB is another vector. So, let us say one vector is AC and another vector is AB. So, these two vectors, this is U and this is V. So, AB and so they define a parallelogram. Any two vectors define a parallelogram by drawing a vector parallel to this and then. So, if you recall your vector algebra, the diagonal of this parallelogram gives you the sum of the two vectors, and it can be proved using purely by geometry that the area of this parallelogram is given by AD minus BC. If A has got the vector components AB and B has component CD, then the area of this parallelogram purely by geometry considerations, by drawing lines perpendicular and so on, and looking at congruence of triangles and using the concept that the area of a triangle is half base into height, one can come to the conclusion that this area of this parallelogram is given by the AD minus BC. This is pure geometry. If we interchange the order of U and V, you will see that the area comes out as minus of AD minus BC, which was earlier. This also relates to what we call as the left handed system or the right hand system in the plane. You go from left to right clockwise or anti-clockwise. So, one can call AD minus BC as the signed area, because area is normally taken as positive every time. So, our starting point is given two vectors U and V, we have the area of the parallelogram. So, PUV denotes the area of the parallelogram. Now, this concept of area, geometric area, has very nice properties. The first property is that if the two vectors coincide, this should be U here, PUU, if the two vectors U and V coincide, then there is no parallelogram, then the area is 0. So, if the two vectors U and V are same, then this is a typo here, it should be PUU equal to 0. The second important property is that if you scale one of the vectors, either U or V, so multiplied by a scalar lambda, so you stretch, right, U by lambda, then the area also gets stretched by the same factor. So, algebraically we can say that the area P of the lambda u v is lambda times the area of, and similarly the other variable, if you stretch v by lambda, then the area again gets stretched by lambda. So, the scalar comes out, that is the second property. And there is a third property, namely if I take two vectors u1 and u2 and add them, I get a new vector u1 plus u2, and I can form the parallelogram given by u1 plus u2 and v. Then it is easy to see from the geometry, I will just show you that this area is same as area of u1 and v, parallelogram u1 and v, and the area of the parallelogram spanned by u2 and v. That is quite easy to see. If this is AB is u1 and BC is u2, then the vector sum is A to C, this is u1 plus u2, and the area of the parallelogram, this is u. So, what is the area of that, what is the parallelogram, that is A, P, R and C. So, that is the parallelogram. Now, it is quite easy to show that this triangle here is same as this triangle, is congruent to this triangle, I can move it there. So, what is this area of the parallelogram, the upper one and the lower one, these are precisely area of u, v and u and u1 and v and u2 of v. So, that geometrically you can see here we are using the fact that the area, geometric concept of area is an additive function. If you do not have, if you have two non overlapping regions, the areas of the union is equal to area of the sum of the areas. So, that property is used. So, but basically important thing is, so the area of the parallelogram u1 plus u2 and v is same as area of u1 v parallelogram and parallelogram u2 v. And similarly, the other variable you can have addition of vectors in the second variable, the same property which is holding. So, in a sense what you can say, see the scalar lambda came out and sum is equal to the parallelogram spanned by the sum is equal to sum of the corresponding areas. So, it is a kind of linearity property which is coming out. So, this is what is called the linearity property of. So, one says this is the area of spanned by two vectors u and v is linear in each variable u and v, in each variable it is linear. So, this way of interpreting motivates us a definition. So, you can think of u and v as the row vectors of a matrix. So, that is 2 by 2. Okay. So, we generalize this to a n by n matrix. So, given a matrix n by n square matrix with real entries, let us say its rows are R1a and Rna, these are the rows of this n cross n matrix. Then the determinant is a function which is defined for every matrix, it is something like the area of the parallelogram, keep that in mind. The determinant of A is equal to 0 if two rows are identical. If in the matrix two rows are identical, then one of the defining properties says that the determinant should be equal to 0. It is something saying in the plane, if u is equal to v, then there is no parallelogram, the area is 0. And the second property is the linearity property, that if one row, say rith row, if the ith row of A is a linear combination of some other row vectors alpha r1 dash ri dash plus beta of ri dash. So, the ith row here is a linear combination of two vectors, then the determinant of A is alpha times determinant of a matrix B plus beta times determinant of matrix C. What is B here? B is the same as A, except at the ith place the row is ri dash, and in C is every other row is same except where the linearity is being given, that is ri double dash. So, only at ith place the rows are ri dash and ri double dash, everything else is same. So, that says that if in a row it is a linearity, a linear combination, then the corresponding values are linearly added. So, if the ith row is alpha ri dash plus beta ri double dash, then determinant of A is alpha of determinant of B plus beta determinant of C. So, where as I said this B is the ith row is R I dash, and in C the rith row is R I double dash. That is the only difference, everything else is same as the rows of A. So, this property you can say that there is a linearity in each one of the row vectors. This function is linear in each of the row vectors, because determinant of A is dependent on the rows R1, R2, Rn. So, if at some place it is a linear combination, then the corresponding thing is reflected in the right hand side. It becomes a linear combination of the corresponding matrices. So, that is linearity. So, one is, the first one was, if two rows are identical, then it is 0. That is something similar to saying that if parallelogram two sides are identical, then there is no parallelogram, area is 0. And second is linearity in each variable. And the third one is what is called a normalization constant. That means, for identity matrix we define determinant to be equal to 1, right. There is just a normalizing factor, nothing more. So, you could put anything you like, but normally it is a good idea to have determinant of identity matrix to be equal to. So, there are three properties which are defining determinant. One, the first property said that if there are two rows which are identical in a matrix, then its determinant is equal to 0. Second property, if a row is a linear combination of some vectors, then determinant of that matrix is a linear combination of the corresponding matrices coming from the linear relations. And third is normalization, namely determinant of identity matrix n cross n is equal to 1, right. So, what we are going to do is, using these defining properties alone, these three properties, we are going to deduce all other properties of determinants that you might have been using earlier, right. So, these are the properties which define determinant, and everything else can be deduced from these three basic properties. That is what we want to show. So, sometimes instead of writing the letter D of a matrix A, one also puts two bars around A, right. This symbol also is used to indicate you are looking at the determinant of the matrix A, a notation only, nothing more than that. Is it clear? Three definitions, they are perfectly taken from the concept of area of a parallelogram. Area of the parallelogram is 0 if u and v coincide, there is no parallelogram. It is linear in each of the variable. If u is u1, u2, u1 plus u2, then correspondingly the area is of u1 with u1 and with plus with u2. And if you scalar stretch each side, then the area gets accordingly stretched, right. So, those are the three. So, that stretching and the sum is put together as linearity, put together as the property of linearity. So, these three properties. So, let us look at the first one, that if A is a n cross n matrix of course order bigger than 2, for 1 there is nothing to prove, and if we interchange two rows of the matrix, you will get a new matrix, right. The claim is that the determinant of this new matrix is minus the determinant of the original. You must have used this property for determinants left and right. So, what we are going to do is, we are going to show that this property is a consequence of those three properties. So, let us see how is that. So, let us assume I is less than j, right. Ith is interchanged with j. So, one of them will be smaller than the other. So, let us say ith row is smaller than the jth row. So, now let us consider a matrix B. So, what is I am constructing a new matrix B. This matrix has all rows same as that of A, except for ith and jth. What is the ith row? That is Ri plus Rj of the original one, and the jth row is also same as that of Ri plus Rj. Ri and Rj were interchanged. So, using that I and j, I have constructed a new matrix, right. Now, in this new matrix, ith and jth row are same, right. What is the ith row for this matrix now? Ri plus Rj of A. What is the jth row? That also is. So, what is the determinant of this matrix by definition? What will be the determinant of the matrix be? By the very first property, if two rows are identical, then it should be 0. So, determinant of B is 0, right. Okay. Let us have a matrix C, where I and jth row are not for every k not equal to I and j, the rows are same as that of A, right. But the I jth row I am putting both as Ri. Again there are two identical rows, right. And similarly the matrix P, where the jth row is same identical, that is the jth row of. Okay. So, all these three will have determinant 0, right, because in each one of them the two rows are identical. Now, what is the relation between B, C and P and A? Let us compute that. What is B equal to? There is a linear combination coming here, right, in the ith as well as the jth row. There is a linear combination. Ith row is Ri plus Rj of A, and jth also is Ri plus Rj, right. So, use the property 2 of linearity. What I will get? So, we will get the following: determinant of B, which is 0, right, it is same as determinant of A plus determinant of C plus determinant of P plus determinant of A dash. Why is that? At the ith place Ri plus Rj, at jth place also Ri plus Rj. So, how many linear combination will come? I, J, Ij and Ji, 4 will come. So, these are the 4 here. A is the original one, Ij, right, DC is II, this is JJ identical, and A dash is I and J are interchange, right. So, using property of linearity, determinant of B, which had I plus J and I plus J, that is 0. So, that is equal to this. D of C is 0, D of P is 0. So, what is it? D of A plus D of A dash. If these are 0, so what is D of A? That is minus D of, right, A dash. So, we have used the first two properties, namely if two rows are identical, then it is 0. If there is a linear combination, you get the linear combination of the corresponding matrices. So, using only those two properties, we have proved the theorem, namely if you interchange any two rows of a matrix, then you get a negative sign. The negative sign is introduced in the value of the, and this is purely without expanding or doing anything. We have just used those three properties, right. Okay. So, let us, is it clear? Proof? Okay. Let us look at 2, which says another property, that if two rows of a matrix are linearly dependent, matrix is written as row vectors R1, R2, Rn, that ith row will be a linear combination of the remaining one, then what will happen? If it is a linear combination, what will happen? When I expand by using linearity, two rows will be coming identical, right, in the expanded one, in the linearity, right. Supposing the ith row is dependent on the first and the last, say 1 and n. So, what will be the Ri equal to? It will be some alpha times R1 plus some beta times Rn, right. Now, when I expand it, what will happen? R1 and R1 will be coming, and Rn and Rn will be coming in the expanded on the right hand side, right, using linearity. So, those will be all 0, right. So, determinant of a matrix in which at one row is a linear combination of the other rows vectors, that means same as saying it is linearly dependent on the other ones, then the determinant of that matrix is 0. That is the second property there. Again using only linearity, nothing more. The fact being used is a vector is dependent on the others if it is a linear combination. So, if you put that linear combination and expand, you will get two rows identical in the expanded ones. So, all will be equal to 0. So, determinant vanishes. That vanishes means it does not disappear, right. That means determinant is equal to 0. A better word is determinant of that matrix is 0. Okay. It is a very loose English saying the determinant vanishes, okay. It does not disappear, it becomes 0. So, here is the proof. Okay. So, if ith row is a linear combination of the remaining ones, right, then when I expand, look at each of the expanded matrix, there the rows, 2 rows will be coming identical in Bk. So, all will be 0. So, this will be equal to 0, right. Is it okay? Clear? Or shall I write in 3 by 3 and show you again? Yes, you want to? Okay, let us show it, write it in 3 by 3. So, let us take a matrix A, which is R1 here, R2 here and R3 here, right. Let us say R2 is a linear combination of R1 and R3. They are dependent. So, one of them will be, say, let us say R2 is a linear combination. So, what is R2 equal to? Alpha R1 plus beta R2. So, what is A equal to? So, implies what is A? R1 alpha R1 plus beta R2 R3, right. So, here is a linear combination coming. So, by determinant property, what is determinant of A equal to? It is alpha times determinant of the matrix R1, R1 and R3, right, plus beta times determinant of, I should put determinant of the matrix R1, oh sorry, this was R2 was a linear combination, so it should have been R3. R1 is a combination of R1 and R3. So, I wrote a mistake here, it should have been R3. So, it is R1, R3 and R3, right. So, what is this determinant? That is 0 because R1, R1. This determinant is 0 because R3 and R3. So, I have used the linearity property, scalar comes out and this is a linear combination. So, it is a linear combination of R1, R1, R3 plus R1, R3 and R3, right, that is linearity property. So, this is 0. So, this is equal to alpha multiplied by 0 plus beta multiplied by 0. And same thing for a general one writes this way, whatever. So, the jth one is a linear combination of the remaining ones. So, you construct those matrices here because only 2 were there. So, we got 2 terms, right, otherwise you will get except for k not equal to y, all other will be appearing and each one of them will be a matrix with 0 determinant because 2 rows will be identical in each one of them, right. So, this gives you the property that if 2 rows of matrix are linearly, or if if the set of vectors are linearly dependent, then one of them will be linear combination. You can write that also. It's clear, only those 2 properties are used.